I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on standing waves, speed, wavelength, frequency, and period. So in this video, we're going to talk about standing waves, which is speed, wavelength, frequency, and period, and how all of those are related. So first, what is a standing wave? So a standing wave is when pulses are generated from one end of a spring and they continue to reflect inverted from a fixed end, and they come back, they're going to interfere with the generated pulses. And those pulses continually interfere with each other as pulses are generated from one end and reflecting off of the other. So what happens then is if the rate at which the pulses are generated is an exact value for the string, then what's going to happen is a wave pattern forms. So this is what a standing wave looks like. So if we have pulses that are generated from the left end and they're reflected off of the free end, then what happens is you have those pulses continually interfering with each other, where we have points of destructive and constructive interference all along that wave. Now, when this happens, this is called a standing wave. Now, if we look a little bit further into standing waves, and we're going to talk about some vocabulary. So we're going to pause that wave, and we're going to look at some points along the wave. We're going to draw first our equilibrium line, which goes right through the center. So the equilibrium line helps us find the amplitude of the wave pulses. Remember, amplitude is the height from the equilibrium to the highest point. Now we also have places called a node, and the nodes are the red dots, and that's the place where generated and reflected waves have destructive interference. So there's no displacement or no movement of the string at all along those points, as you saw in the standing wave. The spring was just oscillating back and forth. Now we also have an antinode, and that's the place where we have constructive interference. That's the place of maximum displacement, which has the largest amplitude. So the antinode is the constructive interference, and the node is going to be where we have our destructive interference going on with our reflected and generated pulses. Now we also have wavelength, which the Greek letter lambda is the symbol, and that is the distance between two consecutive crests, which is the highest point, or it's the distance between two consecutive troughs, which are the lowest point of the wave. Now remember, in the standing wave, crests become troughs and troughs become crests, and they oscillate back and forth. Now another way to think about wavelength, it's the point in which a wave starts to repeat. So if we look, we start at a crest, we go through a node, down to a trough, back up to a node, and then back to a crest. At that point is when it starts to repeat. Same thing for a trough to a node to a crest, back to a node to a trough. That's the point where it starts to repeat. And wavelength is measured in meters. Now we can also find the wavelength. The distance between two consecutive nodes is half of a wavelength. So if we count in this situation, we have half a wavelength between those first two nodes, and then we can continue to count those half wavelengths. So we have another half wavelength between the second and third, another half, another half. So we've got 4 half wavelengths in that total length, which is going to help us to calculate some values for our standing waves a little bit later on in this video. Now, some more vocabulary that we need to know is frequency. So we're going to set that back in motion, and our spring is now oscillating, and then we have our frequency. So if we have pulses being generated on the left end, it's the rate at which those pulses are generated, or it's an event that's occurring per second. So a pulse being generated per second. Now, if we time this for 10 seconds and we count, we can see that this oscillates 4 times in 10 seconds. So to calculate the frequency, we'd take 4 divided by 10, which would be 0.4. So our frequency would have a value of 0.4. Now, the unit for frequency, since it's a rate, it's going to be 0.4 per second, or 1 over seconds is also known as hertz. That's the unit for frequency. Now, the period of a wave is the amount of time it takes for a wave to complete one cycle, and that's measured in seconds. So one cycle, if we look at that first antinode, when it goes from being a crest to a trough back to a crest, that is one oscillation. So we can time that value and see that would be the period of the wave. Now we can also calculate the period of a wave, And the period is capital T, and that's going to equal 1 divided by the frequency, or 1 divided by our value of 0.4 that we timed. And 1 divided by 0.4 would be 2.5 seconds. So it takes 2.5 seconds for a crest to go from a crest to a trough back to a crest. And that's how we calculate frequency and period. Now, frequency, wavelength, and speed are all related. So wavelength, measured in meters, and is going to equal the value of the speed of the wave in a medium in meters per second, and that is going to be divided by the frequency of the wave. Now remember that the speed of the wave can only change when the medium changes. Now when the medium changes, the speed changes, but one of those other values is going to change, which is the wavelength. The wavelength changes and speed change in a medium change, but the frequency stays the same. So when a wave goes from one spring into another, the speed and wavelength both change, but frequency remains the same. Let's look at an example problem now. So we've got a spring that is stretched to be 6 meters long. The spring is a mass of 1 kilogram and its unstretched length is 2 meters. And a standing wave is created with 6 nodes using a wave generator that produces 10 pulses per second. And we want to know what is the tension in the spring in this situation. So let's break down this problem. We've got 6 nodes. So first we're going to make a drawing of a standing wave with 6 nodes. So we can see we've got 6 red dots. That's the point where our nodes are. No displacement of the spring. And we know that that's going to oscillate back and forth between the black and the gray lines. Now we can add in our equilibrium line from one end to another, and we know that that distance is going to be 6 meters. Now we also have some information that we know the mass is 1 kilogram and is 2 meters long when it's unstretched. That's going to help us find the linear density of the spring, which we know from a previous video that tension force has an equation with linear density in it, so we're going to need this value as well. Now, we also have another value of 10 pulses per second. Well, that's an event per time, which is going to be our frequency. 10 pulses are created every second, so our frequency is going to be 10 hertz. Now, looking at our distance, we know that the length is 6 meters, so that total length from end to end is 6 meters, and we're trying to find the tension force. And the equation we know for tension force is that the speed is equal to the square root of the tension force divided by the linear density. Well, in this equation, we have two unknowns. We don't know the speed, and we don't know the tension force. So we're going to need to bring in another equation for speed. So the wavelength is equal to speed divided by the frequency. So we have two equations that have speed, so we can rearrange our wavelength equation to solve for speed. And with both equations now being solved for the same variable, we can substitute wavelength times frequency in for speed, and wavelength times frequency equals our square root of tension divided by the linear density. Now the wavelength, we still don't know that, so we still have two unknowns. But what we do know is we have 6 nodes. So what we can do is count out our half wavelengths. So we have a total of 5 half wavelengths from end to end. So 5 half wavelengths is going to equal the total length of the spring. So we can find our wavelength just rearranging this equation. We know that the wavelength is going to be 2/5 the length of this spring. So we can substitute in 6 for our length and find that the wavelength is 2.4 meters. Now we know the wavelength, so the only unknown in this equation we have is the tension force. So we can rearrange this equation for tension force by squaring both sides and then multiplying by the linear density, which is going to give us an equation of tension force is going to equal the wavelength times frequency squared multiplied by the linear density. So now we're ready to substitute our numbers in. So we can tension force is equal to our wavelength, which is 2.4 meters, which we just found. Our frequency, that's going to be a value of 10 hertz because that's 10 pulses generated per second. Those two quantities multiply together and then we square them. To find the linear density, we need to know the mass of the spring, which was given as 1 kilogram, and the unstretched length. This is important. It's the unstretched length, not the length of the string when it's stretched. So that's 2 meters. And then we can evaluate and get 288 newtons. So when a spring that has a linear density of 0.5 kilograms per meter is stretched 6 meters long with a tension of 288 newtons and a frequency of 10 hertz, that is going to produce a standing wave with 6 nodes. So, this is an introduction to standing waves. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below, subscribe to my channel, Cabby Coaches, and follow me on Instagram and X at Cabby